Okay, in the previous session, we have talked about this basic principles of the breathing system and Mapleson A circuit, that is Mackle circuit. And we can go through this with a very general idea. Shall I ask a few questions regarding this last session? The piece or in correct question to answer this. So, Mapleson systems are classified. This Mapleson system classified according to the afferent reservoir system and the efferent reservoir systems. Suppose Mapleson A, B, C or afferent reservoir systems. That means what do you mean by the term afferent reservoir system? The reservoir bag is situated in front of the limb. They do not have the efferent limb as the APL valve is at the patient end. So take this Mapleson A. The reservoir bag is in the receiving point of the first gas flow. That is the afferent system. Afferents from machine to the patient towards. That is in the sense of inspirative path. So they do not have the efferent limb as APL valve as the patient end, except in the lax system. And the afferent reservoir systems are efficient during spontaneous ventilation. If we take this afferent reservoir system, these systems are very, very efficient in spontaneous ventilation, providing APL valve is separated from the first gas flow by more than the patient's tidal volume. And in case of Mapleson A, so these systems are inefficient during control ventilation, requiring fresh gas flow 3 times the minute ventilation. So if we take this, afferent reservoir systems means the reservoir bag in the afferent limb. And the afferent reservoir systems are A, B, and C. The efferent reservoir systems D, E, F, that is the class today. Mapleson D, E, F or efferent reservoir systems derived from as TPs. Without the reservoir, the TPs requires fresh gas flow greater than the patient's peak inspirative flow. That is, which may exceed 60 liters per minute in order to prevent entertainment. So a reservoir or a tubing or a bag that is situated in the efferent limb, expiratory limb, to reduce the fresh gas flow requirements. So providing the reservoir volume is greater than the patient's tidal volume, the system will be efficient for control ventilation. And DEF for control ventilation. The mechanics are complicated, but they will almost always be something rebreathing, and they can maintain the normal apnea achieved with the fresh gas flow around equal to the almost just 1 time or 1.5 times the minute ventilation of the patient. And these systems are not efficient in spontaneous ventilation, which requires the fresh gas flow of 2 to more than 3 times the minute ventilation of the patient. So that is the basic difference between the ABC and DEF, afferent reservoir system and efferent reservoir system. Okay. Now we go to the slides. What do you mean by afferent and efferent? I have already told about this. And describe the assembly of B and C system. That is the B, Mapleson B and C are not at all routinely used now. It is not in common usage. The fresh gas flow is there. This is the fresh gas flow. I'm rowing. And the APL valve are at the patient end of the tubing, which causes the complex mixing of fresh and expired gas. So it is that is why if you take the patient is expiring, see that the patient is expiring, the expired gas will go through this APL valve, provided the bag is full or the expired gas will enter into the reservoir tubing and the reservoir bag, and the fresh gas flow will expel the gases through the APL valve, which is present inside this mixed alveolar gas here and not here. And the system is not at all well versed in expelling or venting the mixed alveolar gas. That is why the Mapleson B system is a failure. With this Mapleson C, there is no hosing is present here. No hosing is present here. And reservoir bag and fresh gas flow and APL valve and the patient N. The system is similar to Mapleson B except this tubing, and it is inefficient for both spontaneous and controlled ventilation, and it requires more than 2 to 3 times the minute ventilation of the patient, and it is not at all used. But very rarely this Mapleson C system is used in resuscitation. It's an alternative to a self-inflating bag, and it is not commonly used in these two systems, and we can skip these systems and we can directly go to the system, Mapleson system D, E, and F. So Mapleson B, no use at all, and Mapleson C, if at all used, you can use the system for transport of the patient from ICU to somewhere else or during resuscitation, except these systems are not at all useful. Okay. Why it is not commonly used, I have already told. High flow of gas are needed to prevent rebreathing of carbon dioxide. Therefore, air theater pollution is maximum, and fresh gas flow required is equal to the peak inspirative flow, which we cannot able to keep up with our boils machine, and there is a lot of wastage of gases. So the systems are not at all used now. And what is the configuration of this D system? What is the configuration? And D system, here the common thing in D, E, and F are almost the TPs here. Take this area, the TPs 1, 2, and 3. These 3 ends are there: patient port, fresh gas flow port, and venting port. And these are unique for the system of D to F. Here, the classic form of Mapleson D, that is 6 mm tube that is supplies the fresh gas from the machine. It connects the TPs at the patient, and other limb of the T is attached to the whiteboard corrugated tube to the reservoir bag attached here. An expiratory valve here is almost away from the patient, near to the reservoir bag in Mapleson D system. Okay. And what is we are not using this D system very as it is, because there is some modification is done in the D system, and that system is called the Baines modification. Here, what is the modification here? The same thing, APL valve and reservoir bag are almost away from the patient, and the fresh gas flow is getting inside the expiratory corrugated tube, and that will end near the patient. That will end near the patient end. So that is called what is tubing coaxial system. What do you mean by the coaxial arrangement mean? It is tube within the tube, which I have already told. That was explained in LAC system in the previous session. And that is the arrangement. There is a coaxial arrangement is done in Mapleson D, and that is called Baines modification. That is called Baines modification. Why this? Who did this? The McIntosh and Fosk during the Second World War administered anesthesia. It was introduced by Bain and Sporrel in 1972. And what is the assembly of this Bain? What are all the parts here? There is an corrugated tubing with a diameter of 22 mm. That is an expiratory limb having the diameter of 22 mm. And this inner tube for this fresh gas flow is 7 mm. And the total length of this tubing is 1.8 meters. And the outer tube is transparent so that inner tube can be seen, any dislocation and kinking. So this outer tube is transparent, we can see what is inside the tube. And you can modify the tube lengthening in remote locations according to our need in head and neck surgeries or anesthesia and remote situations. We can modify the tube length. And that is the modification done in Mapleson D and anesthesia practice also. And it is the here. See this is the schematic diagram of this vein system, and that is the original intersurgical vein circuit with the APL valve, and the APL valve is connected to the scavenging port is there available. We can connect this APL valve to the scavenging port also. Okay. And here, and you can see this vein modification. The fresh gas supply tube is inside the corrugated tubing, already told here. The fresh gas flow from here to the patient end. And during inhalation, there is the gases from this expired limb and the inhalation tube, that is the inner tube, both are coming to the patient, that we have to note it down. And during exhalation, the arrangement, the assembly in this vein circuit is here. During exhalation, from the patient expired dead space and mixed alveolar gases mixes along with this fresh gas flow. It is inner tube is having this fresh gas flow, and this fresh gas flow goes to the expired limb of the patient there is a mixing. There is a mixing is always there in the vein system. That is the problem in this coaxial arrangement. During inhalation also and during exhalation also, the expired limb gas will be withdrawn inside the patient. That is the thing we have to note it down. And we will, if you understand this one, you can able to easily understand the working principles of this vein system. Okay. What is the long versions of vein usage? If there is anything else, there is Kritika. Kritika is there, can unmute and can answer it.
Good morning.
Good morning. There is any long versions of vein circuit usage? Any idea regarding this?
No, sir.
No. So long versions are there. You can modify the tube lengthening. That is normal lengthening is you can unmute. The normal lengthening is 1.8 meters. And we can change over this. The another version is 2.7 meters and another version is 5.6 meters. You can increase any length of the tube. You can use this vein system in anesthesia and remote locations. You can use this in MRI suites also. And you can have this, the patient is in the one room in the MRI suite. You can sit there in the console room with the veins another end, and you can monitor the patient. Okay, in CT rooms and also there. And another version, this long tube is 2.5 in case of head and neck surgeries, and we are sharing the head end of the patient with the neurosurgeon and our anesthesiologist. So it's a great problem in occupying the space, and we can, with this, using this long version of the vein circuit, you can far away from the surgeon, you can monitor this. So the long versions of vein system is available. Okay. Ventilator can be attached to the vein system, Kritika? Ventilators can be attached to this vein system? Any
Yes,
idea? Where you can attach the ventilator, anesthetic ventilators in the vein circuit? In which place can you attach it?
Sir, in the outlet of the anesthesia machine, sir.
In which place? outlet of the anesthesia machine is wrong, you can, in the brain system, you can have this reservoir bag is there. You can see the figure, reservoir bag is there. You can take away the reservoir bag and the APL valve, shut off this APL valve. You can attach this anesthetic ventilator force into this, and the exhaust valve will be present in the anesthesia machine. Exhaust valve will be anesthesia machine. So this is the area where you can attach these anesthetic ventilators in bench circuit. Okay. See this? You take away this, the patient valve and the exhaust valve. This is the system console of this anesthetic ventilator. It is the corrugated tubings of the ventilator. You can fix it in the place of where the reservoir bag is available. Next. Okay. And we can go to the functional analysis in spontaneous ventilation in the brain system. Functional analysis. We can go to this picture. Before going to this functional analysis, you can understand this picture. Yes, okay. In the inspiration, there is a, you can understand this, then only you can go for this the schematic diagram and functional analysis. In fresh gas, flow is coming to the patient and the gas in the expiratory limb also coming to the patient during expiration, what I told earlier. During expiration, the fresh gas flow and the gas from the expired gas from the patient goes to the expired limb. You mean this expiratory limb or the expiratory tubing or expiratory forcing, whatever it may be. During expiration, the reverse will occur. And what happens during the expiratory pause? What happens during the expiratory pause? How? And there is nothing from the patient because the patient is in a pause state, and the fresh gas flow is going to the expiratory limb to vent the gases, vent the mixed alveolar gases which are all present in the expiratory limb. And that is the point of care, that is the point of issue, the point of concentration is here. What is that is here, you can understand the role of fresh gas flow to venting out what are all the gases present in the expired limb. Otherwise, if it is not vented properly, what happens? During expiration, whatever the limb will be sucked inside the patient during the act of next inspiration. And that is why the role of fresh gas flow is most important in the efficiency of this system. Okay. Here this, now you can understand these schematic diagrams of this functional analysis of the bench circuit brain system during spontaneous ventilation. See this, the first respiration, see the figure A, the appropriate gas flow enters as close to the patient, end of the breathing system, and the system including the reservoir bag will is filled during the first inspiration. So the first inspiration, whatever the gas present here, whatever the gas present here in the expiratory limb and the fresh gas flow all come to this, no problem at all. And if the inspiratory rate, I mean this peak inspiratory pressure is equal to the fresh gas flow, the gases present in the expiratory limb, that is here and here, will not be taken care of. But it is not possible. And we cannot set the fresh gas flow as equal to the patient's peak inspiratory flow rate, which is roughly about more than 40 to 60 liter per minute, which is not possible. Our Boyle's machine will not give 40 to 60 liter per minute at the flow rate. And whatever the gases will be sucked inside and the bag will collapse during the first act of inspiration. So during expiration, what happens? The exhaled gases, first gas coming through this is an dead space gas which cannot take part in the alveolar gas exchange. So that is almost equal to that of fresh gas flow. There is no alteration in the composition of air. Okay, can you able to follow me? And that will first enter into this expiratory limb. And the fresh gas flow is also coming there. The direction of the flow is here. The fresh gas flow also delivered into the expiratory limb, pushing, and that what happens? They displace any fresh gas remaining here and start to fill the reservoir gas first. And the pressure is mounted up well, that will release the pressure in the APL valve, and whatever the gases here and here also vented out. So of the expired gases, those from the patient's respiratory dead space voided first, and then the gases from the mixed alveolar gas, that is those gas that will take part in the alveolar gases exchange. There is a mixed alveolar gas that will also next vented out, provided the bag is filled and the pressure is mounted up. Now you can now understand the role of fresh gas flow. How much should be there to push all those things and filling the bag and venting all the gases into the venting out the atmosphere by opening the APL valve. That is why, and this is, I'll come to the next letter. And point number C here is, there is the patient in expiratory pause. That is most important. That patient in expiratory pause is most important because it has a very major role. That is most important role in fixing the efficiency of the system. During end expiratory pause, the fresh gas entering the system passes down the void bore. Here the pause is there, expiratory pause. There is no gas is expired from the patient, and only fresh gas flow is coming here and pushing. What is here inside, that is very near to the fresh gas flow, what is there is the mixed alveolar gas, and next is the dead space gas, and the dead space gas is filled by this the reservoir bag, and the pressure in the system, the gas flow is very continuous. The pressure in the system is high enough to open the APL valve and the gas is vented out. The amount of fresh gas occupying and stored in the patient's void bore hose at the end of expiration, that is for the next inspiration, that will depends on what? Now you can able to understand it, this function analysis. So next inspiration, the patient is getting from fresh gas and FGF and the gas present in the expiratory limb. So what is the gas present in the expiratory limb determines the rebreathing. How much it is vented out, that determines the rebreathing. So that depends on the fresh gas flow rate, number one, and number two, the duration of the expiratory pause. The pause is more, and venting out, it will vent almost most of the gases to the expiratory limb. This stage, the pause stage, the expiratory pause is more time, it will vent almost all the gases. I mean, almost all the mixed alveolar gases. And number 3, degree of mixing, that is the turbulence of the gas present here. We cannot pinpoint out up to this level there is a dead space gas, and up to this level there is an mixed alveolar gas. We cannot assume it because the gas flow is very turbulent. So the turbulence of the gas, these are the 3 factors that will determine and what the quality of the air that is drawn inside the patient during the next act of inspiration. And able to understand this? So the next inspiration, the inhaled gases consist of initially of this stored fresh gas and mixture of exhaled gases in the tube. And sometimes the possibility of, because the peak inspirative flow rate is not at all met out by this exhaled limb, the gas in the reservoir bag also drawn by the patient during the act of next inspiration. So this is one of the somewhat in a complicated phenomena regarding this analysis of this vein system. That is why we are so much bothered about the fresh gas flow and the expiratory pause, which is the most important stanza in working principles of this vein system, because that will vent the most of the mixed alveolar gases by this means of this fresh gas flow. The time needed for the expiratory pause is most important, and the flow rate, the fresh gas flow rate is also most important to venting out the gases. So in the same picture, that is a complicated one. The same picture in controlled ventilation, what happens? In controlled ventilation, what happens? In the first inspiration, there is no problem at all. In the first inspiration, there is no problem at all. As the bag is squeezed, we are squeezing the bag here in controlled ventilation. The fresh gas flow entering the system, as well as the squeeze, this gas will come through this expiratory limb along with the fresh gas flow that are all inhaled. But during expiration, what happens? Patient is expiring not on its own. The mixture of fresh gas flow and exhaled gases, the mixture of fresh gas flow and the expired gases are coming to this, eventually entering the now partially deflated. Here the reservoir bag is deflated in controlled ventilation. They will reach the deflated reservoir bag to fill this. That will have, and during this expiratory pause, so during the act of expiration, can you able to follow me? The patient's exhaled gases and fresh gas flow enter into the exhaled hose, and it will fill the partially collapsed bag. During expiratory pause, next figure, what happens at this point, provided the time of expiratory pause, the fresh gas flow is continuously flowing here, and will push the gases of the mixed alveolar gases and the dead space gas here. And if the bag is filled, the pressure in the system is adequate enough to open the APL valve, and that was vented out. See this? This is the most important critical point. Everybody should have to understand this. The duration of the expiratory pause is most important to venting out the rebreathed gas. I mean the mixed Okay, sorry for the interruption. Okay. So at the time of this next inspiration, sorry, what is there in this reservoir bag during this? Just before the next act of inspiration is the reservoir bag is filled with dead space gas and mixed alveolar gas and some fresh gas also. And if the system that was, and how much the air in the reservoir limb, I mean this expiratory limb is vented out, that determines the composition of air that was drawn inside the patient for the act of next inspiration. How much it is vented out, that determines. So for the next inspiration, the next piece of the reservoir bag, the continuing of fresh gas flow plus the fresh gas flow stored in the fresh gas flow stored in the expiratory limb. There is the reservoir limb, expiratory limb. That will come into play, role in next inspiration. So for the next squeeze of the bag, the continuing fresh gas flow, this one, and the fresh gas now stored in the breathing hose. Any previously expired gases that may remain in the hose may pass into this patient, while some of the mixed gas in the bag escape via the. And during the act of the squeezing, the system is very much, and some of the gases present here, it will circuit. Vein system is unstable. I don't know why. I'm audible now. I'm audible. Hello, I'm
Yes, sir.
audible.
Yes, sir. Audible, sir. Audible, sir.
Okay.
Voice is breaking, sir. Voice breaking, sir.
Voice is breaking. I don't know. The internet problem is there. The connection is unstable. Now it is okay now. No problem. So this is the functional analysis of vein system during this spontaneous and controlled ventilation, that you have to analyze it. You can go and read now this Dorson or Watt's principles of anesthetic instruments. You can now understand this functional analysis. And this is the analysis. We can go to the next slide. What are the factors that influence inspiratory mixture? What are the factors? There are many factors that I have already told is the fresh gas flow. That is the most important factor. And the respiratory rate is another important factor, because higher the rate, what happens to the pause? The space between the time between the inspiration and expiration is very low, and we cannot vent out the gases present in the corrugated hose. So the respiratory rate has the most important role. And number 3 is the expiratory pause. So we have to give the adequate expiratory pause for venting out the gases. Then only the fresh gas flow will vent out all the gases and mixed alveolar and dead space gases into the apial valve. So the expiratory pause has this important role. And the tidal volume. This patient should have the low tidal volume. I mean adequate tidal volume. So the increase in the respiratory rate, what happens? The tidal volume is reduced. Tidal volume is reduced, increasing the rate. Again, it will have the impact on this expiratory pause also. And larger the tidal volume, more gases, and increasing the pressure into the circuit is very good, and that itself will open the apial valve and the gases will be vented out. So with this, that is why the fresh gas flow should be very high to vent out the gases present in the reservoir limb. I mean the exhaled limb. corrugated tubing. That should be more than 2 times our minute ventilation. So the factors are these 4. In control ventilation, I have already told. First picture, second picture, I already told it is late. The squeezing the bag, some of the gases vented out, and the gas really goes through this exhaled limb and mixed first gas flow. Both will be get inside the patient during the act of expiration. Patient expired gas and first gas flow come to this exhaled limb and partially fills the bag. Once the bag is filled and the pressure is mounted up, and that will open the valve and that will be vented out. During the act of expiratory pause, what happens? There is no gas from the patient, only fresh gas flow that will push this mixed alveolar gas present the exhaled limb, and that will open up the APL valve to get out, vented out, and some of the gas will get enter into the reservoir bag also. So rebreathing is inevitable, almost we cannot dare share about it. And during the next act of inspiration, what happens? We are squeezing the bag and the pressure mounted in the system is very high, and that it will self open the APL valve, and some of the gas will be vented out during inspiration, and these gases and fresh gas flow both all get inside the patients during the act of next breathing. See here, the pure white is the fresh gas, pure white here, and the dark shadow, light dark shadow is a mixed alveolar gas, this one. Here, this one. And very good dark, deep dark is a pure alveolar gas. There is a gas that will take part in the gaseous exchange. What are the basic principles to prevent rebreathing in both spontaneous and controlled ventilation? Anybody else can able to answer this question? Rifan, what is the basic principles to prevent this?
Sir, the fresh gas flow and the respiratory rate, sir.
Oh, okay. So the basic principles, what is you have to purge the gas, vent the gases that will present in the expiratory limb. That thing to be handed over, number 1, because they are the culprit for the next act of inspiration. They will be sucked inside during the act of next inspiration, and rebreathing is taken care of. So the purging, venting of the gases in the expiratory limb, I mean this reservoir hose, is most important, number 1. And number 2, supplement the stored gases in the breathing course so that any mixed gas in the reservoir bag is prevented from reaching this patient. So here, what Rifan said is most important. The fresh gas flow required always is greater than the patient's minute volume, because that is the volume, that fresh gas flow that will push the contents present in the reservoir limb to vented out. That is largely dependent on the expiratory pause. The longer the pause and more effective will be the ability of the fresh gas to purge the breathing course of expired gases. So the basic principles are, the long expiratory pause is most important. So when you are ventilating this brain circuit using for GA, you should not increase the respiratory rate. You should have the adequate time between the expiration and inspiration. You should have adequate time. In the meantime, the fresh gas flow will be venting out the mixed alveolar gas and the dead space gas present in the expiratory limb of the brain circuit. What is this? So here, this histogram, isoplugs are there. Isoplug means showing the occurrence of this. See this curves. These are all studied with the vein circuit. The isopleth represents the constant PCO2 levels or maintained by changing these two things. One is the fresh gas flow, VF, and this VE is the minute ventilation. See this? The isopleth represents the fresh gas flow. The same PO2 can be achieved here. See 6.7 kPa, kilopascals, and 5.3 kilopascals, and 3 kilopascals. From the fresh gas flow from 100 to 240 ml per kg per minute. We are having this, see this, take this isopleth, see this 6.7 kilopascal of carbon dioxide, PCO2 level. They are having this 150, the fresh gas flow rate, and they are maintaining this minute ventilation of 100. The PCO2 maintained will be 6.7. And with this, next, take this next isopleth, having this 150 fresh gas flow, and thereby we can reducing this alveolar ventilation of 100. That's all. That is enough for maintaining the PCO2 of 5.3 kilopascals. So there are two factors. By altering this, we can get the same value of PCO2 levels. I mean this fresh gas flow and this alveolar ventilation. This is a study that was taken for the efficiency of the Mapleson D system used in controlled ventilation. That is why Mapleson D system is best for controlled ventilation, and Mapleson A is not. It is only for this spontaneous ventilation. Can you use ventilator? I have already told earlier. There is a where we can use this ventilator. You can take away this APL valve and this the place where the reservoir bag is present. You can take off it and you can attach the ventilator hose to here, and you can utilize this anesthesia ventilator during this your vein circuit. No problem at all. And the patient exhaust valves are where is APL valve? The APL valve will be taken care by the anesthesia machine. These anesthetic ventilators, the exhaust valves are there. What are the hazards of the vein system? Anybody else?
Sir, there may be in the inner fresh gas flow tube may be kink or may detached at times, which is not noticeable. Even if the tube is kinked or if detached, the bag continues to be filling, so that we may mislead.
Okay.
The patient will receive only the alveolar gases again, no fresh gas flow, which is dangerous, sir. Then no scavenging system, sir. So pollution will be there, sir.
Okay. Here, what we said is very correct. Exactly, very good. It is internal tube kink. There will prevent fresh gas being delivered to the patient. Suppose the internal tube is kinked. What happens? See this picture. See this picture earlier. What I told. Suppose the tube is kinked somewhere else here. And what happens? The patient is taking breath from whatever the gases present in the exhaled breathing hose. It is very, very dangerous. The patient is taking again and again the CO2 accumulated, inspired gases, and hypercarbia will mount that will endanger the patient. Okay. So kinking of this inner tube, the inner tube integrity is most important point of view, whether the system is efficiently working or not. Otherwise, the patient will get very dangerous situation. Okay. Yes. And next one. Sometimes the internal tube can be disconnected. Sometimes it may be a manufactured defect also. Suppose disconnected, what happens? There is a large dead space resulting in hypoxemia and hypercarbia. And the movement of the reservoir back during spontaneous ventilation is not therefore indication of fresh gas is delivered to the patient. So you have to monitor in patient on spontaneous ventilation. You can monitor this reservoir bag, okay, that is moving during each act of inspiration. But in case of we are using the circuit for controlled ventilation, the situation is enormously dangerous. And our monitors can only denote that there is a hypoxemia with any attachment of this entitled CO2 monitors are available, then only we can able to recognize it earlier. Otherwise, it will come on very dangerous end to the patient. So that is the most important hazards of this brain system. Okay. How will you check this brain system? That is most important. Very minimally is there. How will you check the brain circuit?
Sir, to check the integrity of the inner tube, Pethick's test is followed, sir.
Can you explain it what it is?
Sir, we have to occlude the patient in and using an oxygen flush. If the inner tube is patent, due to Venturi effect, after removing the end, the bag will deflate, sir. But
You are
if
occluding the
leak
tube.
in-
You are occluding the which tube for Pethick test? You are occluding the tube.
Sir, patient end.
Patient end you are occluded.
Then we have to use oxygen flush, sir. Then after removing, we have if the inner tube is patent, due to Venturi effect, the air will be sucked, so the bag will deflate, sir.
The reservoir bag is collapsed.
Yes, sir.
Am I correct?
Yes,
Okay.
sir.
Next, any other thing?
Other test we have to with the end of the syringe or with we have to open the inner tube. We have to flush. Then the flow meter will dip, sir.
No, you are not very clear. I think you cannot able to understand the test significance of the test. You are putting where and what?
Sir, the other test can be performed by using a low flow of oxygen, sir.
Low flow oxygen is opened.
Okay.
How much low
Then
flow?
with
You are giving is 500 ml per minute. Okay. You are opening the
Then,
low flow. Okay. Then
you are occluding the inner tube with the finger or the barrel of the syringe.
occluding the inner tube with the barrel of the syringe. Okay.
Then we have to observe for the flow meter indicator, sir.
What happens to the flow meter indicator?
That flow meter will dip, sir.
Why the flow meter is dipping? Why the flow meter is dipping? Okay, then any other test? And commenting, as like that of in your Mapleson A system, Mapleson decision checked for leaks by occluding the patient end, closing the APL valve and pressurize the system. And that is the test for this outer tube check. That is the whole system checking. The APL valve is then open. The bag should deflate easily if the valve is working properly. This is the very commonest thing. Okay. And then what is called checking the integrity of the inner tube of the veins. That is what Kannan told is low flow oxygen flow meter, occluding the inner tube with the finger at the barrel. And the inner tube will what is already told earlier, very good. And Pethick test you have told earlier, there will eventually affect. Okay, thank you. How it is used in online ventilation? This bench circuit can be used in online ventilation. Any idea regarding this? And this question was asked by the examiner of the North. Yeah, Kritika is the senior most qualified anesthesiologist. Can you use this bench circuit for online ventilation strategies? Any idea?
No, sir.
No. You can use this non-dependent lung. Dependent lung we are connecting, and non-dependent lung we are not partially deflate this lung for better oxygenation. You can use this bench circuit by providing CPAP. Okay. During one lung ventilation, using a double lumen tube, a modified Mapleson D system is attached to the lumen, leading to non-dependent lung used to apply for the CPAP to maintain partially inflating the operating lung field to prevent hypoxemia during one lung ventilation. Okay. What are all the advantages of the bench system? Niveta is there or not? What are the advantages? What are the advantages of this bench system?
Sir, it is best for controlled ventilation, sir.
Best for controlled ventilation. Good.
Yes, and it's lightweight and coaxial arrangement, which is very useful for convenient to use.
Coaxial arrangement is convenient for use. In what way it is convenient? Coaxial arrangement. What do you mean by the term coaxial arrangement?
Sir, inner tube under tube arrangement.
Tube inside the tube.
Yes, sir.
The flow of gas is in the same axis. That is coaxial. Tube within the tube. Okay.
Yes, sir.
In what way it is advantageous?
So there is sometimes a warmth that is added to the inhaled gases, sir. So that the warmth added to the inhaled gas by the exhaled gas that passing through the outer tube, sir. So that is
Excellent
also one
answer.
of
Excellent answer. Very good. Very good. Okay. And then, so the tube inside the tube, they will produce moisture to the patient, and
Yes,
there will be the humidification effect is most beneficial to the patient. Okay. It is a lightweight and minimal drag and ET compared to the McGill circuit. It has a low resistance, and the outer tube is transparent, easy to detect any kinking or disconnection of the inner tube. It can be used during both spontaneous and controlled ventilation, and changeover is very easier. It can be useful in non-accessible areas. It is MRI suits, and exhaled gases do not accumulate nearing surgical field, so risk of flash fires is abolished. It's a very rare advantage. And it is easy for scavenging gases because the APL valve is there. You can, with this APL valve, you can connect a hose to the scavenging system. Thereby, you can reduce the air pollution. Okay. And Mapleson A system is used. The scavenging is very tough because the APL valve is near the patient end. If you put anything more on this, and it will drag over it, it will be very hindrance to the anesthesiologist, and there is a malposition of the tube, and so many problems will occur. Okay. And easy to connect to the ventilator, the bench circuit, which I have already told earlier. There is some warming of the inspired gas, what Niveta already told. This gas and moisture and humidification effect is very much with our bench circuit. That is all the advantages of this bench system. What are the disadvantages we already discussed about? Anybody else quickly say, Niveta, what are the disadvantages?
Again, due to the coaxial nature, there will be a disconnection or pinking of the tube. And sometimes the leak, if any, it could be missed because of that system, sir.
So the leaks or disconnection can be missed earlier because provided the patient is on controlled ventilation. Okay.
Yes, sir.
And then?
And there is no scavenging system. So there will be a pollution possible. And also the entire corrugated tube, there is a large dead space, sir. If this occurs, if there disconnection occurs, the entire corrugated tube, it becomes the large dead space. And because of that, there is hypercarbia and hypoxia, sir.
So the length of the tubing has the major role
Yes, sir.
for creating a dead space. Oh, okay. So due to the multiple connections due to multiple circuit, there is a risk of disconnections, which is very common. And wrong assembly of the parts will lead on to malfunction of the circuit, then tetrapollution, what I already told, very good. And increase the cost due to high fresh gas flow. That is the most hitting topic because we are a wastage of gases, and economy is not user friendly, and increased cost and wastage of gases. And there is a kinking already told, inner block lead on to hypoxemia and hypercarbia. And there is we cannot any mild crack or any gas leakages, we cannot able to point it out. That is possible in coaxial system arrangement. And metal head, some case report is there. And it cannot be used in pediatric patient with less than of 20 kg. And vein circuit less than of 20 kg, it is not ideal because of the why we cannot use this pediatric patient. Niveta, can you use this vein circuit for pediatric? Can you use it?
Yes, sir. Not less than 20 kg. We haven't used.
Why? Why you are not using this for pediatric patient? You can, the bag is so much big, you can attach a pediatric bag of 0.5 liter. And because of the very large dead space in the pediatrics dead space to be avoided. That is why we have specially designed this Mapleson E and F system for pediatric patient where the dead space is very, very low. Okay. And then go to the next area. And Mapleson E system, this ISTPs, can you able to see this ISTPs? This ISTP system, who invented it and described this assembly? Who is there? Gopal. Gopal is there? Hello, Gopal. Who invented this ISTPs? Dhanlakshmi.
Sir, good morning, sir.
And when? Good morning. You are in sleepy mode. What is the question I have asked?
Who invented RCP, sir?
At which year? And what is the assembly? What are all the ports there in ISTP system?
3 ports, sir.
What are they? Who invented? So this ISTP system is invented by Philip Hoyer in 1937. You are not prepared. That consists of initially that original model is a metal tube of 1 centimeter in diameter. The examiner will ask you this. The older examiners, the old people are coming here about more than 55 to 60 years old. They are more fond of this ISTP system. Is the original version of this. It is 5 centimeter in length and 1 centimeter in diameter with a side arm. Used as a function as a non-rebreathing system, fresh gas enters through this side arm. So see that the fresh gas enters through this side arm only. And another port for the patient and another port for the reservoir tubing. That is the arrangement assembly of this ISTP system. Okay. Describe the configuration. Dhanlakshmi, what is the configuration of Mapleson E?
Sir,
Sir, what you are doing is, are following me or not?
Yes, sir. Following, sir.
Can you describe this configuration?
Sir, in the ISTPs, there is no reservoir bag, sir. Only the corrugated tube and the fresh gas flow and the patient end is present, sir.
And the expiratory port can be closed in a chamber from which gases are evacuated. This is the the Mapleson E system. There is
Yes,
a
sir.
TP system with the patient end and the fresh gas flow. And for the machine end, there is an expiratory limb is attached, corrugated expiratory hose that is attached. Okay. And what is the techniques of use here? Here I will follow this. The same thing, follow this picture here. And for the patient end, during inspiration, there is a gas from the reservoir tubing and first gas flow will come to this. And during expiration, what I have told earlier in the D system, D, E, and F both are same, all work as in TP system. And during expiration, and the fresh gas flow and patient expired air will enter into the reservoir limb. That you have to remember it to understand the working principle. And during expiratory pause, what happens? Only fresh gas flow enters the reservoir tubing. If you understand these three sentences, and the understanding of the working principle is very, very simple. For spontaneous respiration, expiratory limb is open to atmosphere. Spontaneous respiration, expiratory limb is open. For controlled ventilation can be performed by intermittently occluding the expiratory limb and allowing the fresh gas flow to inflate the lung. So you have to occlude this reservoir tubing during controlled ventilation. But assisted respiration, it is very difficult to perform. You have to coincide with the patient's each phases of respiration, and according to that you have to occlude and open this reservoir bag, which is very, very tough job, and it is not at all clinically practically possible in assisted respiration. Okay, what is Jackson-Rees modification? Dhanlakshmi, you have to. What is Jackson-Rees modification?
In the Jackson-Rees modification, reservoir bag is present, sir. This can be used for pediatric patients, controlled ventilation, sir. And
Not for spontaneous, only for controlled.
both can be used for spontaneous and controlled ventilation, sir.
You mentioned this only controlled.
No, sir. Both can be used for spontaneous and controlled ventilation, sir.
Only can you describe the bag of Jackson-Rees modification? What is the speciality of the bag?
This reservoir bag is 500 ml, sir. There is capacity.
The pediatric 500 ml. That is a standard. Below that, there is no bag is available, madam. Only 500 is the least capacity of reservoir bag available. Okay.
Sir, in the reservoir bag, the end is the tailed tip is present, sir.
Tailed tip open.
Yes,
so reservoir double-blinded open bag.
Yes, sir.
Double-blinded
okay.
APL valve.
Is
there in the Rees modification? APL valve?
Is present at the end of the bag, sir.
Usually no, there is no APL valve, as the Rees, Jackson-Rees has not included this APL valve here because pediatric system is a valveless system. Any valve inside any circuit that will produce resistance. Actually, there is no valve present in the pediatric circuits is concerned, but later on there are so many additions by this. And they are added this initially, they added the beater valve, and then next they will put an APL valve also now. There are so much of modifications, okay. So initially, this is the original version of this Jackson-Rees modification by double-ended open blind reservoir bag is attached to the expiratory limb of the patient. And there is a port for expiratory fresh gas flow that is very near to the patient. So there is a TP system attached to the expiratory limb, and this expiratory limb is attached to the double-ended blind open reservoir bag. Okay, Good. And it may be fitted to the device to prevent bag from collapsing while at the same time allowing excess gas to escape. What is the idea of this bag? Dhanlakshmi, what is the idea of this bag attached to this expiratory limb of the patient? The circuit.
We can see whether the baby is in the spontaneous mode. The bag helps in assisting the ventilation, sir.
It bag helps us and monitor for the patient.
Yes, sir. Whether
How
the
much
baby
tidal volume is dropped inside. You can use a visual monitor for spontaneous anesthesia, spontaneous expiration, number 1. And number 2?
Helps in assisting the ventilation, sir.
Helps in assisting ventilation. Okay, number 2. Good. Number 3. So by partially occluding the reservoir bag during this controlled ventilation, you can create a CPAP effect on the patient. So CPAP effect is most important and expected thing in pediatric ventilation is concerned, because there is the only one procedure that will increase the FRC of the patient. Actually, the pediatric patient having the FRC are very low compared to the adult patients, and this FRC will increase, the CPAP will increase the FRC, functional residual capacity. Okay, that is, these are the 3 advantages of adding just bag inside the circuit. Thank you. And can you use this scavenging in pediatric patients? Nowadays, there is a APL valve is attached there, producing scavenging, producing enormous resistance to the pediatric patients. There are so much of modifications of that. Scavenging we performed by enclosing the bag in the chamber from which waste gas are suctioned by attaching various devices to the relief mechanism in the bag, APL valve. These intersurgical people are modifying so much of things in this Mapleson F. They are putting APL valve just near to the patient to provide protection from high pressure. There are so many modifications are going on with this original system. Okay, what is the functional analysis? Come to this. Dhanlakshmi has to answer for this. Can you describe the functional analysis in Mapleson E system? Just 3 sentences for these 3 pictures, and I will add later.
During inspiration, sir, the fresh gas enters.
During inspiration,
the fresh gas enters from both from the corrugated tube and also from the fresh gas flow to the patient, sir. During expiration, the expired gases and the mixed alveolar gases vented out via the expiratory limb, via the corrugated tube, sir. During the expiratory pass, only the fresh, since the fresh gas flow is flowing, the fresh gas flow enters the corrugated tube, sir.
And then for the next respiration?
For the next
inspiration?
For the next inspiration, minimal amount of expired gases and the fresh gas flow enters the patient.
So, for the next inspiration, there is a fresh gas flow plus the gas present in the expired limb. I mean, this reservoir limb is drawn inside. Is it?
Yes, sir.
Hello?
Yes, sir.
Hello, Dhanlakshmi?
Sir.
Is there or not? Gone
Yes,
out?
sir.
So what happens here in case of spontaneous ventilation? So in the next act of inspiration, what happens?
Minimal amount of expired gases. And
why they have to take the next act of inspiration? They are drawing. See this picture B is for first inspiration. For the first inspiration, what I have already explained it, and this bench circuit also, the same thing happened in pediatric circuit only, because D, E, F, all these three systems act as a TP system. And the system, Gopal is another, Gopal. And the gas flow and the gases present in the reservoir limb comes through this. And during expiration, I will shortly say there is gases from first gas coming through this patient is the dead space gas, which has the composition almost near to the first gas flow that will first comes out, and then next is the mixed alveolar gas, the gas which takes part in the alveolar gas exchange, and then next get inside into the respiratory expired limb. And all those things, this first gas flow is most important because it will push or vent out all the gases present here in the expired limb to the atmosphere. That is voided to the atmosphere. And the next is the during expiratory pause, there is no gas from the patient side, only first gas flow flows into the expired limb and venting the gases present in this. What is the first gas? Here is the mixed alveolar gas, and next one is the dead space gas, all will be vented out. And there is the functional analysis during spontaneous ventilation. Here, that is the patient's inspiration, whether during the act of inspiration, the first gas flow is adequate enough for the patient. No, it is not adequate because the peak inspiratory flow rate is 30 liters per minute. The inspiration of 0.5 seconds. We are using this 2 to 3 times this minute ventilation of first gas flow. That is roughly about total flow first gas flow of 4 to 6 to 7 liters per minute. It may be. But the patient's peak inspiratory flow rate is 30 liters per minute. It will not meet out the demand of higher first gas flow. It will not meet out the demand of first gas flow only. That is why the gases in the expired limb also be drawn inside. That is the problem here. That is why whatever the gases present in the expiratory pause, during the period of expiratory pause, should be voided out. Otherwise, the gases present here will be initially this mixed alveolar gas and dead space gas will be drawn inside. So the first gas flow has the most important role in prevent rebreathing in spontaneous ventilation in pediatric patients. So during the period of expiratory pause only, the first gas flow will vent out all the gases present in the expiratory limb. The diameter of this reservoir limb must be sufficient to present the lowest possible resistance to the pediatric patient. The diameter should be lowest resistance possible. And the resistance should be, for the neonate, should be less than 1 centimeter of water. Usually in adult, the resistance offered by this valve present in the apial valve, that is about, if it is fully opened, what is the resistance offered by this apial valve is, the recommendation by ASTM standard is 1 centimeter of water and maximum up to 2 centimeter of water. Here there is no valve here. This tube will produce a resistance in pediatric and neonate. That diameter of the tube is most important value, number 1. And number 2 point in functional analysis consideration is concerned, and the volume of the expiratory limb, the volume of the reservoir limb, otherwise called reservoir limb or expiratory limb, that is this one, that should be not less than the tidal volume of the patient. Suppose, if you understand this reservoir limb is more than the tidal volume of the patient, long and lengthy comparison with this tidal volume of this pediatric infant, which is very low. So whatever the gases will be present will not be vented out to the atmosphere, and during the act of next inspiration, whatever the gases present will be sucked inside, that will produce rebreathing. So the lengthier the tube, I mean this longer the tidal volume of the patient, there is a possibility of rebreathing during the next step of inspiration. Suppose the tube is so small, tube is like this only, this level, less than the tidal volume of the patient, what happens? When the next step of inspiration, the FGF is already, I already told earlier, FGF is not adequate enough, and whatever present here will be drawn inside, and the volume is so small, and air will entrain from this atmosphere, producing air dilution. So the two problems are there with this. It's a rebreathing, and number 2 is air dilution. That is according to the volume and length of the reservoir limb in Mapleson E and F systems. And the optimum first gas flow depends not only on the patient's minute volume and respiratory rate, but also on the capacity of the reservoir limb. Suppose if later the least of the patient tidal volume, then the rate of 2.5 times the minute ventilation is sufficient. It is the most satisfactory arrangement. It is the most satisfactory arrangement in this Mapleson E and F system is concerned. However, if the capacity of the reservoir is reduced, the flow rate must be increased enormously. Otherwise, the air dilution will occur. Suppose there is no corrugated tube, then Lakshmi, if there is no reservoir limb is present,
Sir,
what happens?
air entrainment, sir. Air dilution occurs, sir.
Air dilution. Air dilution means what?
More amount of
What do you
air.
understand with?
More
What
amount of
happens
air.
there? That speed is very low, I think. Audible now. Can I proceed?
Proceed, sir. Audible.
Yeah. Okay. This is the picture I already told earlier. What happens during inspiration, where the patient gets gases, and during expiration, what happens, and during expiratory pause, what happens. These 3 pictures are most important for understanding this functional analysis. And rebreathing in Jackson-Rees modification, there is a spontaneous ventilation. There is no rebreathing will occur if there is no exhalation. What I have told earlier with Dhanlakshmi. If there is no hose, there is no rebreathing. If there is an expiratory limb and the first gas needed to prevent rebreathing will be as same as like the Mapleson B system, that is the 2 to 3 times the minute ventilation of the patient. And during controlled ventilation, there can be no rebreathing because only first gas will inflate the lungs. And regarding air dilution is concerned, no air dilution occur during controlled ventilation. There is no possibility. And during spontaneous ventilation, air dilution cannot occur if the volume of the tubing is greater than the patient's tidal volume, which I have told earlier. If there is no respiratory limb, expiratory limb, if the volume of the limb is less than the patient's tidal volume, there
dilution can be prevented by what will you do? You have to do increase the fresh gas flow, exceeds the peak inspiratory flow. So the fresh gas flow two times the minute volume, and the reservoir limb should be at least 1/3 of the tidal volume of the patient. But the now latest recommendation is the expiratory limb, that is the reservoir limb, is equal to the patient's tidal volume to prevent air dilution. Okay. What are the hazards of this Mapleson E? We are using this intermittently, occluding the expiratory limb, because we are not having this what is called bag is not there. There is the overinflation of the lung. There is every possibility of direct trauma. That is the hazards in Mapleson E system. And can you use Cassini filters in Mapleson E and F? It is possible. That is heat exchange moisture. You have to insert between the patient and the TP system. Again, the problem is the resistance. It will enormously increase the resistance of the patient, which is not at all warranted in pediatric anesthesia is concerned. What are the advantages and disadvantages of this Mapleson E and F system? It is a very easy assembly, light, portable, inexpensive, low resistance system. There is no absence of valves. This is the question commonly asked by the examiner. And this disadvantages, which I will told earlier, direct trauma occurring during controlled ventilation in Mapleson E due to overinflation. And because the anesthetic doesn't have the feel of the bag in Mapleson E. And it is not the problem seen with the Mapleson F, because there is a bag is inside the Mapleson F system. And high gas flow is needed that will lead on to atmospheric pollution and theater pollution, and wastage of gases, and economy is not there. It is there is no economy. There is a loss of gas, and humidification of gas does not occur because there is no coaxial circuits are present in the pediatric systems. That is Mapleson E and F system is concerned. And we can have the respiratory gas monitoring in Mapleson circuits. Where will you, in general, Mapleson circuit, what is the ideal place? This is the common question asked by the examiner. In Mapleson circuits, where will you put the respiratory gas monitoring probes? What are the ideal sites for monitoring these respiratory probes? Any idea, Kritika? Any idea? Where will you attach it? So all of the Mapleson system, A system has the press gas inlet near the patient's connection port, except A. So this makes it difficult to get a reliable sample of exhaled gases. Near to the patient end, we are having this respiratory press gas flow, and there is an alteration in the exhaled gases. So what is the site? These are the sites. Number one site is the exhaled gases and press gas flow coming through this, which I have told earlier, this picture. During expiration, the gases from the press gas flow and exhaled gases, and the patient from the expired gases goes to the exhaled limb of the patient. I mean the reservoir limbs or exhaled limbs. And what happens? The press gas flow is very high. If you put like this place, you cannot get the correct reading of it. Measurement is not adequate. And number 2, 3 and 4 sides, this side and this side. This is the elbow connector and the tracheal tube connector. Near the tracheal tube connector and the elbow tube connector, if you put this gas sampling monitors here, these sides 3 and 4 are ideal for respiratory gas monitoring in Mapleson system is concerned for better results. But the problem is, if you put the probes here, that will increase the weight of the patient, it will drag, and there is instability of malposition of the tracheal tubes and connectors are possible, and there is a kicking of the tube is possible, especially in the pediatric age group. Okay. And coming to the end of this, what are the advantages of the Mapleson system? And I will finish it. There is very simple and costly. Less costly, components are easy to disassembly and can be disinfected, sterilized, very cheaper, and it is because of this cheaper you can dispose this patient for once the patient we are used for this patient, they are very lightweight, they do not cause any drag on the tracheal tube. And the length of the Mapleson B system can be increased to whatever you need, and there is suitable for anesthesia in remote locations also. And amplification of the gas is possible with the coaxial systems, and resistance of the system is very low, so they are good for spontaneous respiration. And but if the APL valve is not open properly, it adds to a resistance. The only resistance caused by this system is the APL valve. And if it is more towards the patient, it is very problem. But if the APL valve is towards the machine, it is not at all much problem at all in venting the gases. And there is no possibility of toxic production of gases. I mean, compound A can be produced by circle system is used along with the sevoflurane, which is not possible. And carbon monoxide that is produced with the desflurane in circle system is along with the desflurane, which is not possible with this using this Mapleson A system. Mapleson systems are concerned. Regarding disorderlies, first gas flow required for the circuit is very, very high. It has a very increased cost. There is no economy of gases. There is a pollution is there definitely. Due to high fresh gas flow, inspired heat and humidity tend to be very less, and humidification of the gas is required separately. Otherwise, dry gases will be insufflated to the patient lung, producing these effects of drying. There are so many effects of drying are there, and optimum fresh gas flow is difficult to ascertain. If it is lowered by any cause, it can result in rebreathing. There is a problem. And Mapleson ABC systems, APL valve is close to the patient, and scavenging is very, very difficult. And there is extra assembly will drag the patient a little, demorphize the stability of the tracheal tube and the connectors. And Mapleson E air dilution may be occur because there is a, and Mapleson E there is no bag is there, we cannot able to monitor the spontaneous breathing patients, and they are not suitable for patients with the malignant hypothermia because CO2 wash out only because of the very high fresh gas flow, And in situations like in Western world, hypothermia, malignant hypothermia is very common. Without enormous CO2 production is there in malignant hypothermia, it is not possible to handle the situation of CO2 production in malignant hypothermia in these Mapleson circuits. So we need definitely CO2 absorbance. And carry home message coming to the end, brain system is a coaxial version of Mapleson D, and parallel version exists, and fresh gas flow along the inner tube and exhaled gas goes through the outer tube. And not efficient for spontaneous ventilation because FGF rate is very high, 2 to 3 times the minute ventilation, that is roughly about 150 to 200 ml per kg per minute. And inefficient during controlled ventilation, Mapleson B and first gas required is 70 to 100 ml per kg. Regarding Mapleson B and C systems are concerned, B system has a tubing and reservoir bag, not efficient for both spontaneous and controlled ventilation because of the assembly is not adequate enough. And the B system is most efficient than A system during controlled ventilation, and C system is lightweight and used in resuscitation situation. C system. Still now they are using, and patient with the transport, they are using the C system very rare, and it is not very commonly used now. Regarding TPs, the E and F systems are concerned, periodic practice up to 25 to 30 kg. And beyond this, we cannot use it. Why? Because we cannot able to meet out the fresh gas flow that is equal to the meet out the demand of the patient, because we cannot able to meet out the demand of peak inspiratory flow rate of 30 liters per minute, and if we are increasing the weight of the patient and peak inspiratory flow rate is very high, and we cannot able to give it at all. So in periodic practice about less than 25 kg that the system is efficiently works well, and requires high fresh gas flow during spontaneous ventilation 2 to 3 times the minute ventilation, and offers a minimal resistance to expiration, and is a valveless breathing system. And scavenging is somewhat difficult. They have done so much of modification nowadays, demolishing the principle what actually it was produced, And scavenging is more very difficult also. And there is some intersurgical people who are modifying so many things and adding APL valve to the pediatric system, and they are more concerned about this scavenging also. They are most concerned regarding the scavenging and preventing air pollution in Western population. And carry home message, the Mapleson A is the best efficiency for spontaneous ventilation. And for controlled ventilation, it is totally inefficient. It needs high press gas flow to prevent rebreathing. And Mapleson D is the best for controlled ventilation, and Mapleson B and C are very rarely used. And Mapleson D, E, F require high press gas flow to prevent rebreathing. That is the Upfront systems. And ABC, Mapleson ABC or Upfront system, that is regarding the position of the reservoir bag in that decides whether it is afferent or efferent. And they are next in the order of preference list for spontaneous respiration. This Mapleson D2E is best for controlled ventilation and not best for